Okay, let's get started. We were almost finished with class 2, and we had started talking about this definition of nanotechnology, and I kind of told you, isn't it surprising, nanotechnology was actually introduced not by electrical engineers in the lithography area. It was introduced by a traditional mechanical engineer. And so how precision machining went to nanotechnology is kind of the story here for today. And we had come right here, isn't it? We were talking about this man, Taniguchi, who coined the term nanotechnology. And in 1974 used that term to define ultra-precision machining. And so what's the definition of that? He defines it as the process by which the highest possible dimensional accuracy is achieved at a given point in time. And so the curve we're going to look at next, and it's the one we also had in class 1, but I said let's deal with it in class 2 because you will already have learned a little bit more. Huh? So he predicted the accuracies along with the processes or tools to achieve these accuracies. In other words, you know, just like Gordon Moore predicted how the evolution of integrated circuitry would work over time. How many know what Moore's law is? Most of you, right? Can you raise your hand high for those that know Moore's law? Higher, higher. I want to see how many do know that. Moore's law. So can you say loud what is Moore's law?
Computation power doubles every 2 years.
Right, and many other ways it can be expressed. For example, you might have heard that one, that every 2 years the size of a chip, transistor, halves. It's being said in many, many different ways, but it really means that indeed the computing power that comes out of a certain real estate on silicon halves every 2 years. It turns out this is also true in mechanical engineering. They also were able to make smaller and smaller things over time, and that's what he predicted. And not only did he predict the accuracies as a function of time, the year, he also identified what kind of processes or tools you use to achieve these accuracies. And so here is this complicated curve, and I know the letters are a little bit small, especially for people in the back, but I will try to explain what you're looking at. And then once I have introduced that, and I want you to pay attention to this graph, I'm going to ask you a question. And if you can answer that question, you really have paid attention so far, because the answer I have given earlier in this class already, I mean this year, this quarter. So what we are plotting here is the achievable machining accuracy versus the year. Let's say starting in 1900, we couldn't do things that accurate yet, right? And so you see bigger numbers. You also see, so this is the size you can achieve, how small a thing you can make. And this is the year, right? From 1900 going to 2020. And people define machining in different categories. If you use kind of run-of-the-mill tools, not too expensive, you will call that normal machining. And so you could look at a certain year and then extrapolate how good were they in normal machining at that time. Next comes precision machining, and then ultimately, and that's what we'll talk about a little bit for the rest of this class number 2, this is the so-called ultra-precision machining. That is where you really go all out. Very expensive, very good vibration-free tables, the best machining tools, etc. This is the curve that predicts, as a function of the year, what you can achieve. And this is remarkable. You can see that actually one is able to reach nanometers in size. Most people say, oh, you can only do that with integrated circuitry. But you'll see in a moment, I'll show you an example of a robotic CNC machine made in Japan by Fanuc. And can resolve features in the nanometer scale. And so that is what this predicts. You understand that, right? These curves go, of course, you know, become smaller and smaller because our tools get better and better. Now, and this is this axis and this axis. Now look on this axis. what this says is the number of transistors on a chip. And here is again the time. So now we have switched from mechanical, right, machining, to integrated circuits, making chips. And what I'm plotting here is the number of chips, right, the density as a function of time. And that's Moore's law, right? And we said the longer we go, the better we get. That means we can cram more and more chips, transistors on a chip. These two mean the same trend, right? Because if I can put more on a chip, it means they're smaller and smaller. Now, you know, these curves are linked by something. There is one kind of a machine that you have in common in CNC machining and in lithography. And it's that machine, that system, that dictates these accuracies. What is that machine? Almost broader. Your XY table. Remember, we were talking about that, right? Ultimately, if you machine something mechanically or with lithography, you need to be able to position it, move it, and know that movement. And so these two worlds are actually linked, the lithography world and the mechanical machining world. They depend on making the best possible accurate stages. A lot of the machining tools that you see here and the measuring instrument to check how good your machining tool did, we will encounter in this class. So at this point, I'm not going to go in detail to each of those. As we go along this quarter, we will learn about a lot of those tools that you use to achieve these kind of accuracies. The last number we used in terms of how far we were in terms of accuracies. Look, in the 1980s, we got at about 0.1 micron. And so you could find that indeed on that curve. And now let's go a little bit further. By 1993, we could do 0.05 micron. That became possible. And today, there's equipment available featuring 0.01 micrometer and even nanometer step resolution. And unfortunately, it's not all that clear, but that is this Fanuc robotic machine that I was referring to. It costs about $1 million. And this thing here, this is 1 millimeter. And it's unfortunately, the quality of the picture isn't all that great, but this is a famous mask in Japan, a no mask, N-O-H. And check it up on the web, and it's just amazing. These details, this is not done with integrated circuitry technology. It is done with a traditional machining tool with a very fine diamond tip. So if people talk about machining and say, oh, forget about this old-fashioned CNC machining, it's not true. There's been tremendous development there as well. Actually, you know, this machine is not even available in the United States. And why would you do that in a country? Well, if you have a better machine that can make things that no one else can make, you better keep it for a while, right? Because you have a commercial advantage. And so this is kind of a reason why we have this class. We have to start thinking again how we make them better tools to manufacture better. Because that is kind of what gives you the advantage economically as a nation. The final concept for class 2 I want to tell you a little bit about, and I find it interesting, it's this aspect of desktop factory. You know, most of these CNC machines, including the ones you will see here at UCI and learn, you know, you'll see a part being made. These are like 1 ton, 2 ton, you know, the machines can be like from here to there, very, very big. And then often you end up making very small pieces like this. And you can imagine more and people say, why am I doing this, right? Wouldn't it be much better to make a factory that I can put on my desktop? And this concept, this is kind of interesting. This was developed in Japan because they were losing manufacturing jobs faster to China than America lost jobs to Japan so many years ago. You know, so Japan said, what do we do about this onslaught? Can we fight that? And so one of the ideas was if you have everyone able to do manufacturing and the loop between design and manufacturing is very short, there's no reason to outsource. Right? That was one of the thinking behind this. And now, these are already commercial in many stages. And what is the concept? The concept is this. You have this box about this size. And the idea is all that goes in there is power, water, and a material, and the product comes out. And so the idea is you don't build only one of these stations. Maybe the first one polishes a glass. The next one, so that glass part is now put on a little wagon, a little cart, that by a train set goes to the next station. There, that part is unloaded from the train set, and maybe it's etched or something like that. And so it's like building a modular factory with small components. And say you need product XYZ, you look in a catalog and say, okay, I need that station, that station, that station, and you put them together, and you have that train set moving from little desktop factory 1 to 2 to 3, depending on what needs to be done. Now, some people have said, but wait a minute, that sounds good, but will you not lose all the workforce now, right? Because you said, obviously no one can go in the factory, it's too small, right? The idea is it's probably just the opposite. It's just that we will need a much more sophisticated manufacturing person, because he will need to know designing, he will need to know how to operate and run these machines. It's almost like, you know, when the personal computer came, displacing the mainframe, people thought there would be less jobs. Happened at all, right? The opposite happened. Many, many more jobs were created. And this is what we believe will happen also with this, what we call distributed manufacturing. So that basically your Kinkos would allow you to print out or make a 3D object rather than copying your papers. Right? So that was class 2. Any question on this? Well, by the way, this is one of the many desktop factories. There was one in Japan. So before I go to class 3, which is, by the way, quite a bit different. Class 3 is a little bit of motivation and why I got into, how I historically got into this field. But I will start showing additive manufacturing. I will explain 2 processes in the additive manufacturing range. So any questions on class 2? No? Okay. So I hope I don't have that same problem from before. So this class is different. You could almost call it an intermezzo because I gave you a bit of technical information so far, mostly about mechanical machining. Now, very recently, I was invited to give a talk for a series from the National Academy of Science called Distinctive Voices at the Beckman Center. And this pertains so much to this class that I thought, you know, today I will dedicate the time to talk about what I feel is a possible scenario for the future in manufacturing. And I think you will pretty much already understand everything that I'm covering, but as we go along, if there's something you're missing, especially the additive manufacturing, obviously you'll have a lot more material and information about that, okay? So the first thing that I'm talking is my own personal motivation. You know, my field is nanotechnology, micromachining. Why did I get interested since about 2004, 2005 in manufacturing? What's the connection? And so I want to tell you a little bit about that. But then I'm coming to the second point, and this is actually what we're doing here today. We feel that we need to re-engineer engineering classes and courses. We feel that, in a way, we've been on the wrong track. That our students, and we hear that often from industry, say, our students, yet they know the theory, but they cannot apply it. They're not practical enough. And so we want you to have a more balanced set of skills. enough theory, but you also can apply things and make things and figuring out how to make things. And so I will tell you why and how about this re-engineering of engineering. And then the third bullet point, in a way, is a nice fit-in with class 1 and 2, because that was subtractive manufacturing, right? Mechanical machining. Yeah, you're drilling things away, grinding things away. Here, we will talk about additive manufacturing, which is one of the many, many, many names of rapid prototyping. So by now, you're probably confused. 3D printing, there's probably 8 or 9 different words now that really mean the same. So most of you have heard about 3D printing probably, right? Additive manufacturing is kind of really is the same words. Actually, a little bit later, I'll show you a list of about 7 ways you might be. Digital manufacturing is another one, very popular. But it all means the same thing. And what it is, we will explain you today, and we'll show you some devices that have been printed here at UC Irvine. Now, after that, after I'm explaining how this 3D printing works, because unfortunately, we have to be careful. This is probably overhyped right now. You know, you've seen things where they show, I was referring earlier to that, a violin, you know, Stradivarius printed out. I tell you, it probably doesn't make very good music. And also would cost a very, you know, a huge sum. So I will kind of trying to tell the audience here that rapid prototyping, as we know it now, is on the top of the hype cycle, and it needs to go through a lot more transformations, and that will be, we need to be able to machine at multi-length scales, and I will explain what that is. We need to be able to work with many more materials, and we need to do multi-physics, means you cannot only do additive manufacturing, you need to combine different physics forces on the workpiece for us to be able to say, yes, we have a new manufacturing method. And so then some conclusions. In the meantime, you've probably read this rather depressive message here. You know, this is one of the many alarming points people are now making all through the United States, that we ought to get back in manufacturing, or you know, we will lose the economic war and we will become a third-rate nation. So, intro, motivation. I don't like long text, so this time a girl with a very good voice. So this is from a book we wrote around 2004, 2005, and we testified on Capitol Hill about this problem. So, up.
Intro motivation. Countries that are not manufacturing high technology goods anymore are increasingly at a disadvantage because they do not gain the required experience from meeting the newest manufacturing challenges in the production of the latest high-tech products. In other words, the loss of the manufacturing base is not a simple linear loss. It becomes irretrievable, exponential as time goes on. History has shown that it is the manufacturing capability that drives the economical growth and creates wealth. Assuming that we can still market and design new products without manufacturing excellence is naive. One cannot design without knowing the latest materials and manufacturing processes.
Thank you. So, the most important part of this for me is that, you know, when this started happening, you would talk to an MBA or an economist and say, don't worry, you know, we will still make money, we will sell it, and we'll design it. And then what you find out, that's not the truth at all. Because you see, there's something called IP leakage. It means intellectual property leakage. See, your design, you ship it somewhere else, they manufacture it, they learn all kinds of things while they're manufacturing it. And I promise you, they will make the second and third generation product, not you. It will not come back to you. And this is a very, very important thought that escaped many, many people. So, and how I myself felt more and more is this. The government, NSF, NIH, they give billions of dollars in research in the United States. The profits, mostly, recently have gone elsewhere. because we cannot implement our own inventions anymore. And that's scary. We need to reverse that. So a bit more about motivation. I referred to that in class 1 or 2, I think. President Obama announced his Advanced Manufacturing Partnership, AMP. It's a national initiative that enlists the corporation of industry, academia, and the federal government. In other words, he wants to do a little bit like they have in Germany, institutes called Fraunhofer Institute, that do kind of form a bridge between industry and academia to help making manufacturers new and better products. And so he's trying to get, but there's a certain party that does not give it to him, $1 billion to set up 15 such institutes throughout the United States. UC Irvine is trying to get one of these institutes to work on these things. And this point I already made, government investment in R&D is leading to profits elsewhere. Now, this is something probably a lot of you have heard about. What this is showing is the manufacturing employment in the United States. Look what happened here. Suddenly, around 2001, and about now, we lost 1/3 of manufacturing jobs. 1/3 in 8 to 9 years. And it doesn't look like they're coming back. And what is so odd, this is at the same time where, you know, our nanotechnology advances have been fantastic. We are able to write, with an AFM in this case, an atomic force microscope, atom by atom. We have carbon nanotubes. We have CMOS technology that's in the sub 50 nanometer range now. Isn't there like something wrong? Why can we not put more of that to work into the economy and create products? That is, in our opinion, because the gap here is such that we don't make it here anymore, we ship it out, and we don't benefit from our own investment. Right? Is there any questions about this? Do you kind of, it's simple enough in a way, isn't it? So now I come to my second point. The first thing we need to do is you guys, the young people. That is Reengineer Engineering. We have to start thinking, why do all of our young people choose to become bankers? I mean, for a while there, every bright student, the only thing they want to do is get into banking. And what have banks done? They destroyed the world economy. It's true, right? If you're a robber, you can rob one bank. If you have a bank, you rob everyone. No? And so, we need to do something. And by the way, you have to start at home. You have to start with the UC system. I mean, isn't it bad what's happening with the tuition fees? Isn't it bad? I mean, instead of being a public institution, we are about like Stanford in terms of expense. And are we getting more value? Not really, right? Less and less TAs, less and less classes. So we need to work on that. High tuition for what is perceived as less value in the UC system. Unequal access to education. Lack of skilled US technicians for technology companies. On the third point, what we have started doing a lot is this. We believe that there's not enough back and forth between community colleges and four-year colleges. So in my group, you will find that we are now bringing Saddleback students in. And so we'll get more transfer students. Because we need to make the system whole again. You need to have everyone educated. If you're going to develop a new machine, invent a new machine, you have to have the educated technician that can operate it. Right? And fourth, the science of making things got lost in many areas. It was like, making things isn't all that interesting. And we want to change that. I think it's very interesting. You can do extremely fundamental science by making something and learning how you make something in a new way. That was more educational, systemic. Indifference to employees, outsourcing, that makes for a tension in a society. Little interest in making things, real things. I made that point before. And loss of manufacturing bases, loss of innovation. Remember, I used that word IP leakage for that. And then middle class is disappearing in lockstep with loss of manufacturing. And you get a more polarized society with more chances for war, more chances for disease, more chances for everything. Something that the US is actually already responding to are the last 3 points, because this actually really threatens our future. If the US doesn't make, and this is a point that you might appreciate, if the US doesn't make the next big thing anymore, we will also eventually lose the position as leaders in engineering education. We are still the country where everyone wants to come for an engineering education. But if you look at the iPhone and how close Samsung is now beating it, don't you think that eventually people will say, the US is not making the best stuff anymore. I should go there where people know how to make the best stuff, isn't it? Gap between fewer rich and many poor people will continue to increase, because if you don't have good paying manufacturing jobs, what do you think will happen? And then third one, security concerns. Suppose that a war breaks out between US and China, and we need chips to fly our aircraft. We don't make them anymore. We'll have to ask the Chinese to give the chips so we can go bomb them. I mean, you know that I'm exaggerating, right? And I'm trying to make points a bit extreme to clarify it. But there's a point there, isn't there? So that is engineering in the future, we hope. So what we have started doing, at least here at UCI, and you guys are kind of the pioneering class almost, of getting us back into manufacturing. We have named something K2 Gray. Do you know what that could mean, K2 Gray?
Kindergarten to graduation.
Well, and gray, all the way, you know, from already, yeah, man. So we want to re-educate people from K till they old, right? So connect four-year colleges with community colleges that are in turn better integrated with K-12, K-12. Give as broad a group of people as possible access to rapid prototyping, CNC machining, IC clean rooms. In other words, unleash creativity, because intellectual property in manufacturing is much more potent. You see, at university we invent all of these things. You know how many of these patents ever lead to anything? What percentage do you think? It's very small. I don't know if it's that low, but it's very low. On the other hand, if someone is on a manufacturing tool and he fiddles with something, man, his chances of having something that will result in profits are so much higher, right? And we feel that by giving more people access, and that's why I want you guys to know about CNC machining, rapid prototyping. I want you to see what a clean room is, and maybe you'll start thinking about something that you otherwise wouldn't have. The third bullet point is one that I alluded to: shorten the design to prototyping product loop. So if you could indeed sit here and while I'm teaching, come up with a design and you could go home and print it, there's no reason for you to ship it out, right? On top of it, transportation has become so expensive, and when you do outsource, you still often send your engineers to another country, right, to talk back and forth about the design, but that's expensive too. So if you could do it locally, you would be so much better off. Mind you, I'm not becoming paranoid about globalization. I think research, society, culture will continue to become global, but there is no reason not to manufacture local. There's a big difference between that, because you cannot isolate research. Research has to be global. And so this desktop machining I already talked a little bit about, and distributed manufacturing examples. You're in a hospital and you need a knee replacement. You're not going to wait 3-4 days, right, if you're operating and damn it goes wrong. But suppose that next door there's already someone machining the knee that fits a little bit better. That's point of need manufacturing. How the world would change if we could do that. The fourth bullet point, project-based engineering competitions. Maybe some of you know Professor Mike McCarty, right? There's quite a few professors now, besides myself, that are starting to see that if we give students enough tools and let them compete, let them make something. Maybe some of you were involved in the Hoovercraft competition. Does anyone know about that? So we noticed that if you kind of give the students the tools and let them work in group and make them compete to make something, you'll get good results. And actually I will show a little video, and there's some of the actors in that video I see in the audience here, where we did just that. That competition was called Make Your Professor Drunk. And the idea was to print out a bottle opener, and a bottle opener that worked. And so if I opened the bottle without breaking the bottle opener, I had to drink it. And so that was a good competition. We are now also setting up a new department. We hope it will become a new department. Materials and manufacturing technology today is a concentration. We want to convert it into a full-fledged department. And then, as some of you know, and you will actually all go there and work with these folks, we brought Rapidtech onto our campus. And Rapidtech is that entity that has like 25, 30 rapid prototyping machines that you all will learn how to work with. Still a little bit more about, this is still the US. We will not become like Korea or Japan. We are different. There's much more variety in us, much more flexibility, much more freedom. So the changes that we need to bring about need to still be ingrained in how the US typically operates. So flexibility, risk-taking, diversity, imagination, space, and resources. Man, we still have so much, but it's slipping away. And if we build on it, on these points that I'm making, we will still be on top. And you know what? Everyone wants to come to California. Have you noticed that? Were we talking about that a moment ago? But here's the problem. If you want to live in California, it's so expensive, so we also have to have the best educated people. We can't become lazy because we like surfing and the sun, right? So we actually have to do more of an effort to stay on top. So we need to invest in education, new manufacturing materials, and we need to build the next generation of manufacturing tools and methods. Now, I'm going to give you one of the concepts we are playing with. This diagram here, and I'm not going to go in detail, but if you like this field and you're intrigued, you should study it. This is made by a good friend of mine, Professor Placid Ferreira, at Urbana-Champaign. And what he's doing here is term by term comparing a computer with a manufacturing system. And you'd be amazed how many similarities there are. In a way, the biggest problem is this: I can put a digit to the internet, I cannot put a chunk of material to the internet. Otherwise, you can actually make one-by-one comparisons. And this is kind of why we think that we can do the same, just like we moved from mainframe computing to small computers, that we could do the same for manufacturing. So just keep that in mind, and if this quarter you get some ideas on how to further push this, you'd be welcome. Or if someone could work this out in greater detail here, look component by component and just say, but Professor Madou, you're wrong there. That does not equate these two components, the computer part with the manufacturing machine part. Okay? So now, a little bit of teaching. This was like philosophy, right? Wasn't it? Economics, philosophy, sociology, etc. And now we're going to talk a little bit about one technique that people have over the last, about 20 years, but in the last 4 or 5 years it really have, become much more known. That is this 3D printing. Eh? And most of the time that 3D printing was also referred to rapid prototyping. By the way, you remember I said there's all of these names for 3D printing. Look, 3D printing, computer controlled, moldless additive manufacturing. Wow, that's a whole bunch. Eh? So actually, you might not even have understood that first one before this class, isn't it? Now you understand each word of it, right? Computer controlled, well, that's easy. Eh? Next, moldless. We know what molding is now, right? It's moldless, no mold involved. And additive manufacturing. So that's one of the names. Another name, 3D printing, layered manufacturing, digital manufacturing, stereo-lithography, additive manufacturing. It's all the same thing. And here are the commonalities of this approach. Always, you will, again, it's always there, right? You need an XY stage. And when you see these machines here across the street, you will also always find a little table that you're able to control the movement this way, and up and down. So that's where it always starts. A platform that can move in the XY direction, but also in the Z direction. Now, this lady here has on the computer the Eiffel Tower, and here she has her little printer, 3D printer, and she's printing it out. And so I will tell you today, because of the limited time, 2 methods on how that printer could go from this to this physical object. A keyword will always be this slicing. So if you have an object like these glasses and you have them in computer-aided design, what you will do is you will slice it. So you will make cuts through that object, and each of these cuts will be made layer by layer in this station. And I'll show you in a moment how that works. So slicing your object, each slice has a certain thickness, and that layer, that slice, will be made by hardening something or sintering something, and then lowering this stage and put a new layer. Lowering the stage, put a new layer, and on and on and on. So I was telling you about, so I wasn't making up, this Stradivarius was printed. Right? There's too much information on here, and the objective is not to go over all of the different techniques that exist already today. And this diagram will be explained after you've got your practicum. So don't worry about this one. You can say, we'll be informed about what this is after the practicum. But this is a whole list of existing 3D printers. And of that whole list, we will only explain 2 of them. No, sorry, 3. Fused deposition modeling, FDM, 3D printing, and stereo-lithography. The other ones is for later. Okay. How many of you know already a little bit about 3D printing? I know you, Sapna and Mitch. Who else? You've done it? You were also already in Rapidtech, yeah? Great. Who else? Good. That makes it all easier. You were also in the class, right? You were also in the class, right? You were the one making the rocket ship, right? Yeah. So we'll see him soon making his bottle opener. But before we show you what they made, a few more words on how this all works. So I'm looking at the time there. I want to make sure that I at least get to the video and explaining these three techniques. So let's start with fused deposition modeling. The stage, XY stage. So it can move this way, it can move this way, it can also move up and down. Now what I also have, by the way, when I gave this talk last time, what I did is, while I was talking, I had machines building things. And so I could go from this and they say, here, you see it. But so here we have to do it separately, right? You're gonna go see the machine later. So you can see what I'm feeding into this platform here are 2 wires. Think about it, it's like plastic fiber. And these plastic fibers, you see there's 2 colors. One is called the build material, and the other one is called the support material. Now what you do, you feed these wires through this little heating block, and when that material comes out of the heating block, it's molten. And so you have a little bit of a blob of molten material there. Now, since this is an XY stage, I can direct the computer to move that molten material in any shape I want, right? I can draw a circle, I can draw a house, or no, not a house, that's 3D. I can deposit a slice of the house, right? So when I'm finished with slice 1, what do? I lower the platform, computer tells me to write the next slide, But often there's stuff in there, the door needs to open, or need to be able to run through the house. What do? You have that material in here that is support material that you can etch out. Huh? And so after several movements of that stage, you end up with a 3D shape. So fused deposition modeling, FDM technology, was developed by Scott Crump in the late 1980s and commercialized in the 90s by Stratasys. The FDM technology built solid models by melting a continuously supplied plastic wire. The supplied wire typically, so it's often ABS, acrylonitrile butadiene styrene, ABS, which is a thermoplast, and it has a diameter of 0.012 inch, and it's extruded as a hot viscous strand through a fine nozzle. So it's kind of a good way to think about it. It's toothpaste, just squeezing it out and making the outline. All right? And so when you're finished with layer 1, you ask the computer to give you the second slice. So you lower the stage, and it builds the next layer on top of the first one. So a computer controls the nozzle movement along the X and Y axis, and each cross-section of the prototype is produced by melting a plastic filament that solidifies on cooling. By the way, once you have this concept, you will see, to understand how the next one works, it's so much easier. So in this case, it's lines, toothpaste. In another case, it will be powders. So, look. These shapes have not been made separately. These have not been assembled. This was made in one go. You remember how I said that additive manufacturing is very good for very complex parts? Here you get a picture, right? You do not afterwards need to assemble these things. You go to the machine, this is what comes out. So you can use your brain and have the most complex shape in mind, this thing can make it. And so it's especially good for very, very complicated parts. Here, give an example of an application of printing a skull. When you go to Rapid Tech, that's on the 4th floor of the engineering tower. When you open the door, you will see a picture on the wall. And the picture on the wall is of a skull of a soldier in Iraq who was wounded. Not by a gun or something, he had gotten a steel door against his eye socket. And he went blind in that eye. And they couldn't really figure out what had gone wrong. So what they did is they sent the CAT scan to Rapid Tech. This is not the picture, but you'll see it there. And in the picture, it's also hard to see. But once you look at in 3D, you see that there's a part of bone here pushing against the eye socket. So by the time the doctor saw the soldier, he knew exactly where to look and where to do the operation. Think about an important application. All right? So let's see what we have here. After one layer is done, the stage is moved downwards, that's your Z direction, and another layer of deposition starts. FDM features 2 nozzles. One carries the construction material, right, and the other the support material. And that support material can easily be removed afterwards, allowing construction of complex parts. Actually, we'll see in a moment, you can make parts that are moving immediately with teeth that can make movement without assembling anything. So the soluble support material is dissolved in a heated sodium hydroxide solution, and you do some ultrasonic agitation, and so that white stuff here you get out by putting the whole thing in potassium hydroxide, shaking it a bit, and then this dissolves out. Oop. I think I got it almost right. So it extrudes thermoplastic materials. What's thermoplast?
Thermoplast.
Who knows what a thermoplast is compared to a thermoset?
Make cross-link when they cool down, right?
Yeah, so thermoplastic can melt. A thermoset you won't. Huh? So you can, that's why you can only do this with thermoplast, right? Because you need to melt the plastic. Like in spaghetti's coming out. It's moderately fast, inexpensive, and functional parts as feasible. Be careful. When I say functional, what that means is this. This used to be done all the time. People would have a new race car, and they would make a small prototype. But more and more, we are trying to make functional products out of this. That means actually it works. From there, my bottle opener, right? If it's a prototype, it'll break. If it's a functional product, it opens the bottle, right? So ABS, also nylon, can be used, and is often used by mechanical engineers and product developers. These are some machines. This is on the expensive side. It's called the Stratasys Fortus. But then there's actually machinery that can do this for $5,000 nowadays. And there's even less expensive ones. Something that got into the news with that kind of machinery, namely the RepRap, one of the cheaper ones, is this. And this university, they had this machine building this one. So you had like a father and a child. And so that happened in 2008 in Bath University in the United Kingdom. So we saw one, right? One method of 3D printing. Now we're going to see a second one. And you're going to see the similarity between the two methods. So in this case, instead of extruding that plastic molten fiber, imagine this. I have again a stage. Always starts with that stage, right? And I have on the left side, I have a powder, a white powder. And with that roller, I put white powder on the right-hand side, and I make one layer of a powder. If I would blow, I would have it all in my face, right? What I do next, this is so clever. What you do is this. You fill an inkjet printer cartridge with a glue. And that glue can be colored. For example, I color it blue. And now, where the glue is printing on the powder, what happens? The powder sticks. Huh? And I have a layer. So next what I do, I lower the stage a little bit, and I bring again a new layer of white powder over it. Now again, my computer controls my inkjet nozzle, and lets me deposit maybe in another color, blue, yellow. I have another layer that I solidify. And of course, all of that powder that's not been touched by the ink, what happens with it? Yeah, you can recycle it. Nothing has happened with it. So a layer of powder is first, and you can see the powder here, look. He's getting this solid object out of this powder reservoir. These are pretty complex things made this way, isn't it? So layer of powder is first spread out across the built area. An inkjet-like printing of the binder over the part cross-section. I was explaining, right? You go over that first layer and give it the glue or the ink, and it sticks together. You have not, by the way, they often will have to give it a little bit extra sintering afterwards, right, to stick together better, the powder. A repetition of the process with each layer can produce multicolored parts. This is not a good material, rarely functional, so it's mostly to demonstrate things, models, right? And the market leader here, by the way, Z Corp, is gone out of, well, not gone out of business, they've been bought up by 3D Systems. 3D Systems seems to become very aggressive as buying up pretty much all of the other players in 3D printing. More about 3D printing, so all of this has been 3D printed. And you can see, for example, for these molecules for chemical models, very nice, but you will not sit on it or you will not use it as a hammer. It doesn't have, it's not functional. So Z Corporation, no part of 3D System, first introduced high resolution 24-bit color 3D printing, high definition 3D printing. That was in 2005, and they were printing at 600 dpi at that time. The printer accurately and precisely deposits colored binders, and that's that ink, in the desired areas. And then it solidifies the powder in that cross-section of the model. And so here you see some nice typical applications. This is an example of 3D printing. So if I touch this wheel, this one will work. And this is built in one step. Imagine how much work it would be and how difficult it would be to build that any other way. Right? Think back about your CNC machining. There's no way you could do that, right? You would have to take each part, build it, and then really carefully consider how do I put that together, right? Here you see another typical 3D printer and a part being taken out. So all the gears and rods in that demonstration model were created in place as a single unit from bottom to top. At the end of the job, the excess powder was removed between the gears. When any single gear is moved manually, all the others rotate simultaneously. I have to be careful, so I'm going to introduce part of stereolithography, not everything, and then we're going to finish with that movie, and then on Monday, I finish the rest of this class, okay? Because this week and next week is all just class, then the third week, we're going to start doing practica. So, first way of 3D printing was melting of these wires. Second one was kind of sticking powder together with glue. The third one, maybe the one that's best known, is the stereolithography. And here is the inventor. And here you actually see one of the shapes that he built with stereolithography. You will see this one the same in Rapidtech. We have it there. Now, what is the idea here? I love this idea. You have to just think about it. It always has something in common. What do we have always in common? The stage, right? X, Y, and Z. It has this too. In this case, I'm not putting molten lines of plastic on it or a powder. In this case, I submerge my stage right here in a solution, a photopolymer solution. And that solution, when the laser hits it, gets solidified. So now you can imagine I have my stage and I flood it with a very thin layer of that polymer. Now the laser writes in the polymer and solidifies where it hits. Next, what I do, I lower the stage a little bit and a new layer of polymer comes over it. I write in that layer. So it's like 3D writing in a solution. So that is stereolithography. Prototypes and parts are built from a liquid photopolymer, and each part is created by a UV laser. This technique has so much promises because, you see, the better I am at making the small laser spot, the smaller the features is that I can write. I can literally write nano features, and I will show you how nano. Actually, why don't I, because there's a connection with something I told you much earlier. I will come back to all of this, but I can't resist showing you this part. Here. Does that remind you of something? Right. So you remember we were saying at one point, a hair with holes cut in it, subtractive, and I told you later on I will show you adding something to the hair. So I bet you have some of that on your hair. That would be the ultimate, wouldn't it? Just to show off that you're very rich. Look at my head. Anyways, who is this? Who knows who this is? Venus de Milo. Yeah, you were the one that protested so strongly about talking about culture in this class. So, yeah, you were. So, since you had the name right, Venus de Milo, I had another question, but now I'm looking who I asked that question. I bet he's in the back in the class hiding. I was going to ask that person about 300 BC. What was the dominant cultures and what kind of technology was developed at that time? Who was that? Who was going to tell us that? Oh, it was you. That didn't work, did it? Who was it? He was sitting there he was sitting there somewhere, right? Do you know who it was? Anyways, who's taking on that task? We are accumulating all of these questions, right? How do you cut little square holes in a human hair? What's the third way of making a country rich? I forgot my third one so far. What was the third one? That would be the fourth one. 300 BC, that's the third? No, that's the fourth one. I thought there was another one. You're going to do it for us. 300 BC. What were like the key inventions, key technologies, and who made them? So this is done with 2-photon lithography, and we learn about that on Monday. But because of the timing, I will just finish with this little movie showing last year's class in this one practicum, Make Your Professor Drunk. Just a moment, I have to locate the movie. By the way, if you have some questions, ask them now. Yeah.
People on the waitlist going to be able to attend the class once you guys do February?
Yes, they will be, yeah. I will have to do this on Monday. I cannot locate the movie directly. So why don't we finish the class with taking a couple of questions? We have another 10-15 minutes. So yeah, my assumption is that, yeah?
Yeah, I have a question.
Okay, so my assumption is that this is a little bit more comfortable. There's still some people sitting on the side here. It's kind of weird. Normally after the second or third class, my idea was some people will not show up anymore, but that hasn't really worked out. But I will sign up everyone, because I know that some of you will just go on YouTube and see the class, right? And so I have to then think, how do I do that? Because I said the presence in the class is very important, right? So this is where we run into this problem that all academics now face. We put ourselves out of a job, right? Because by next year, maybe I don't have to teach anymore. It's all there. Anyways, I'm sure that will not happen, because I think having the hands-on experience, asking questions and so is so important. So for Monday, I'm looking for a class, a big one. So beyond your Outlook, I hope that by tomorrow, so you'll have an email and know where to come on Monday at 1 o'clock. So yes.
So when you have SLA, how do you put like support material on the? This seems like you can have only like one type of material.
Yeah.
Something, right?
In SLA, unfortunately, you're so limited in the number of materials. And that is one, you know, when I finish this class, I will say, this sounds good, isn't it, and fun. But oh, we have such a long way to go. Especially in SLA, you would like to do this with all type of materials, not just the one they provide you, you know, that's optimized for that photon at that energy. And so material science, to make new materials that can be adapted to that machinery, is a very nice new direction, and people are really looking for that. Any other questions? Yeah.
So how many hours it usually okay to finish our?
Yeah, a very good point. Depending on the complexity and how rough you make it, you might talk about 20 minutes all the way to 8 hours, you know? Because it will depend on your solidification unit, you could call it. Huh? And that's, of course, something that's bad for mass production. Unless, with this technique, you can make the mold. And then the mold, you can make a lot of products out of that. Right? Of course, a mold, you will want metal. And as you've seen, all the techniques I told you so far are powder or plastic. But there is now very good machinery that can sinter metal. And that, of course, you know, for industrial production is very important. Any other question? Yes.
Is this class going to be mostly just in the classroom, or are we at some point going to go into Rapid Tech?
Yeah, you will see, you will be all over. You will be in the clean room, you will be in the CNC machining shop, you will be in one of my labs to do soft lithography. So it's just these 2 first weeks that I'm the only one participating. But then you typically will have, for example, the director of Rapid Tech will come and explain what you will be doing at Rapid Tech. And he will show you how you go from a design to a product. And then you guys, your task will be to make one of these earpieces, a Bluetooth device. And the CNC machining, I already told you, unfortunately, all you'll be able to do there is learn how this person who does CNC machining, how he goes from a file to a product. In soft lithography, again, you will make parts yourself. Right. Yes?
So does that mean that there's going to be time outside of the regular class times?
No, it will always during this class time, but will be another location. And so the people that you will be meeting, Swati Sharma is a senior graduate from my class. She's the TA. You will meet Ed Tackett, the director of Rapid Tech. You will meet Ben Dolan, also at Rapid Tech, and you will meet some of my other students. You will meet people at the clean room, and you will meet Horacio Kido for CNC machining, and so they will be responsible for that. Yes?
Since this is a class that has undergrads and grads, is there going to be any difference in?
Yes, there will be. I will be more demanding for the graduates during this practica that they can better describe, and typically they will lead little teams with undergraduates, and then in the exam they will have 3 or 4 more questions. There will also be in the class one area, I can already tell you where. When we do laser machining, there will be about 6 or 7 slides that only the graduates need to study, not the undergraduates. Those will be more about the physics of how a laser operates. By the way, I just want to make sure there is no new students in this class today, right, who have not been in class 1 or class 2, or are there? Raise your hand if there are students that were not in class 1 or 2. So you're totally new, right? Are there others that have not been in class 1 or 2? Okay. So for the signing up then, so I can do it Monday. You can all sign up, okay? How many still need to sign up? Okay, so let's do it quickly Monday after the class, right?